Everyone. Today I'm glad to share with you our recent work, morphling, fast, near-optimal auto-configuration for cloud-native model serving. We'll first introduce some background information. Large technical companies are now increasingly deploying large machine learning as a service cloud for model training and inference serving. In a typical machine learning as a service workflow, the deployers design and train machine learning models offline with large data sets. The trained models are then published in the cloud to provide online inference services, typically running in containers. And many model serving systems have been deployed to streamline the model deployment in the cloud for improved performance of the service and the reduced cost of the operators. Existing model serving systems support dynamic batching, inference buffering, replica auto-scaling, and auto-selection of model variants. However, we found that efficiently deploy inference services at the container level in the cloud is still challenging. To be specific, given a well-trained model, the cloud operator needs to specify the container-level hardware configurations, such as the resource allocation of the container and the runtime parameters, such as the number of service threads or the maximum batch processing size. These configurations come together to form a large and high-dimensional configuration space. And the choice of these configurations largely determines the model serving performance and the deployment cost. As we can see from this figure, an inefficient model serving configuration in Alibaba cluster yields in very low resource utilization. For example, nearly 80% of the CPU cores and GPU memory size are allocated but not used. In light of these problems, our objective in this project is to design an efficient approach that can quickly find the optimal container-level configurations for model serving instances. And in Alibaba Cloud, we measure a container's serving ability by its peak throughput, defined as maximum requests per second, aka RPS, it can serve without violating the response time SLO. And this peak RPS can be easily measured by using some stress testing tools. And our production system uses this metric to determine the required number of container replicas to serve the service. And given a model serving container, cloud operators need to specify its resource and runtime configurations to quantify how each configuration may affect the serving ability and the deployment cost. We have profiled 42 open source machine learning models in Amazon EC2 cluster and 30 production inference services at our Alibaba cluster. We stress test their peak RPIs under various configurations. And the results are shown in these figures. In this experiment, we found that a good configuration yields over 10 times request throughput than a bad configuration. And we can also observe that there are lots of dimensions of the configurations that may heavily affect your service serving quality. So to formulate this problem, given a well-trained machine learning model, the cloud operators need to find the optimal resource configuration and runtime parameters so that their container performance can be maximized and their deployment cost can be minimized. So formally, consider a configuration vector with m-tunable hyperparameters, and our objective is to find the optimal configuration combinations that maximize the objective function defined as fx. As we can see, it's essentially a hyperparameter tuning problem, and many auto-configuration approaches have been proposed to tune the general cloud workloads. However, we found that none of these works can efficiently solve our problem. First, the common approach is to find the configuration based on the historical data. Notably, Google's autopilot lies on this line. However, we found that the machine learning frameworks such as TensorFlow may occupy all the available GPU memory size when running the machine learning workload. And as a result, monitoring tools like NVIDIA ISMI always observe the full memory usages. So this historical data cannot faithfully predict the actual usage of the resources, especially the expensive GPU resource. And another approach is to sample a small number of configurations in real-world clusters for performance testing. And there are several categories, such as the black box search, like the Bayes optimization, or the white box prediction, like the linear regression methods. Other works may also use similarity-based search, like Google Visor may use transfer learning to speed up their searching process. However, we find that all of these search-based configuration methods may require a large number of samplings before it can search an optimal configuration in our problem. So in this work, we present morphling, a fast and near-optimal auto-configuration framework for cloud-native model serving instances. And our key observation is that the hardware and runtime configurations at the container level have a general performance impact within a wide variety of inference services running different machine learning models. For example, to run an inference service, there is a minimum requirement of the GPU memory size to fully load the serving model itself. And further increasing the GPU memory allocation may enable a potentially larger batch size and hence a higher throughput. Yet, such improvements may diminish as a bottleneck shift from the GPU memory size to other resources, such as the CPU cores. And this motivates a fast auto-configuration approach using meta-learning methods. In particular, we train the meta model offline that captures this common configuration performance train for general inference services. To tune the configuration for a new service, we adapt this meta model with few shot learning and use this adapted model to get the tuning precise. To be more specific, we use the recently developed model-agnostic meta-learning, aka MIMO technique. In particular, morphling trains the meta model offline to capture this general trend, and use this model as the initialization of the learning or search process. Given a new inference service, morphling performs online few-shot learning to adapt this model to a new one and use this to guide the following search process. And we have also implemented morphling's workflow and its algorithms as an easy-to-use auto-configuration service in Kubernetes with around 5,000 lines of Golang code, which is now open-sourced for public access. And morphling is also integrated into kubedl project as a CNCF sandbox project. Morphling exposes the common interfaces that abstract away the heterogeneity of the model serving frameworks and the service deployments. And the users implement these services by specifying the serving model, the tunable configuration parameters, and the optimization objectives. For evaluation, we evaluate morphling on both Amazon EC2 cluster with 42 open-source popular models provided by TensorFlow Model Zoo, including image classification and language processing models. And morphling has also been deployed in Alibaba production cluster as the default auto-configuration service for efficient inference serving at scale. And we also evaluate morphling with 30 real-world production inference services. For the results, morphling can quickly identify the optimal configuration by sampling less than 5% of the large space consisting of over 700 candidates in our open source scenario. In comparison, existing auto-tuning approaches such as the base optimization may require quite larger configurations before it can search the optimum. And morphling's high efficiency is attributed to its ability of quick adapting the meta model to a new inference series. To illustrate this point, we consider tuning two configuration knobs, GPU memory size and maximum batch size, as shown in the figure lying on the right top. And the figure shows that by sampling only a few number of configurations, the performance object and the performance configuration mapping shape can be quickly adapted to the ground truth. Also, the morphling's efficiency is not tied to the particular objective function, but generally applies to a broad range of objectives. To show this, we also defined another two objectives as shown in the figure lying on the right bottom. And this figure shows that under various objectives, morphling can usually get the optimal configuration by sampling only 5% of the configuration spaces. So in conclusion, in this work, we present morphling, an intelligent configuration tuning system for online model serving systems. With meta-learning's knowledge transferring and fast adaptation, morphling efficiently finds the optimal configuration within a large and high-dimensional search space. And morphling's workflow is now open sourced as a Kubernetes services and public on GitHub.